so today is September 24th. And we're going to take a look at section 2-2. All right, and basically it's going to talk about the power rule. All right, so we're actually going to start dealing with some derivatives here. Okay, you did the formal definition of the derivative. What was that? Probably on Monday, right? Where you did the limit of the difference quotient, and it turned out to be a lot of work. All right, we don't want to have to go to that much work every time we calculate a derivative. So you're going to have tons of derivative rules that we're going to take a look at. This is one, okay, and it's going to deal with one specific type of function when we can do this. As we go through, we all know there's more than one type of function, right? We've got polynomial functions, we've got rational functions, we've got ones that have absolute value in them. So we're going to have different rules. So you're not just going to learn one rule to calculate a derivative. You're going to have like a whole group of rules that you will know how to do with different types of functions as you see them, okay? So let's go differentiation rules. Okay, so just in general, all right, we need to know for a fact that the derivative of a constant is 0. Okay, the derivative of a constant is 0. Okay, so in other words, some examples of that, you might see them in like a horizontal line. I could do an equation, y equals 6. All right, well, y equals 6 is a horizontal line, right? But in the pictures and things that we did on Tuesday, that horizontal line, the slope of the tangent line is 0 because it's horizontal. When we sketched the derivative, it dropped down to the x-axis, right? So we know this is a horizontal line, so the derivative has to be 0. The slope of the tangent line is pretty much the derivative. We got to think that through. So notation, y prime tells me that's the derivative is equal to 0. But in general, every time we have a constant, the derivative is 0. It basically drops out. So that's that. Okay, let's do it again because I don't have to do the y notation. I could do f of x. I could do function notation. So let's say f of x equals -4. All right, well, that's still a horizontal line, right? So it's still a constant. I'm taking derivative of it. That slope of that horizontal line is 0. My notation here, f prime of x, that's telling the person, hey, I'm taking the derivative, and it's 0. Okay, so that one's straightforward. That is not the power rule. Okay, that's just something we need to know. All right, now power rule. All right, I'm going to do the official formula that you see in your textbook because I want you to kind of get used to what that notation looks like. All right, you will see the formula in your book as d dx of, say, x raised to the n power. All right, so that's me taking the derivative of a polynomial function, x raised to some number. The formula is going to be n, so my exponent, times x raised to the n minus 1. All right, now stop and think about that. That means subtract 1 from the exponent, right? And then take whatever number was here and pull it down and multiply it by that the coefficient in front. And we saw that. Remember when we were sketching yesterday and I asked you to find the pattern? We did an x squared. You had the graph, and then we were drawing the derivative, and it became a straight line. And then we had the x to the third function. We sketched the derivative, and it became the x squared. So this is where that's coming from. All right, now let's do an example of that. So if I had something as simple as an x to the third, let's make it really, really simple. Okay, my leading coefficient is a 1, right? So I'm going to pull that exponent down. 3 times 1 is 3, and then x squared. So my derivative, you got to use ff prime every time because you're saying, hey, dude, I just calculated my derivative. All right, 3 times 1 gives me a 3 out in front. x squared. So obviously that's just a nice single little example, okay? Now, nothing says that that exponent has to be a whole number or an integer. How about if I had f of x is equal to x to the 1/2? Can I do it even if my exponents are fractions? I can, right? Concept's going to be the same. And again, I'm just doing these examples with one term so we get the hang of it. I'm on my paper, I'm definitely going to go f prime of x because that tells the person, hey, I'm taking the derivative. 1/2 times the imaginary 1 coefficient in front, 1/2 times 1 is just going to be a 1/2 here. X. Now, what's 1/2 minus 1? Do that in your head. 1/2 minus 1. Negative 1/2. Okay, so then I'm going to have a negative 1/2. All right, now, in past, in pre-calc, did I let you leave negative exponents?
Yeah.
No, I did not let you leave negative exponents. Laws of exponents. We got rid of our negative exponents, right? So it's going to be moved down to the bottom. So the 1 stays on top, the 2 stays down there, x to the 1/2 power. All right, and then that's still kind of tacky from algebra 2 going back because we didn't really do radicals. And you're looking at me like, oh my God, I got to go all the way back to algebra 2? Yeah. Can I go from exponential form to radical form really easy? So x to the 1/2 really is square root of x, right? Remember that? Because there's the 2, and then there's the one that we don't write all that stuff in. All right, so generally this is the more accepted answer. Is this technically correct? Yes, this is the better answer. All right, they really like that radical form. All right, now, since we're messing around with laws of exponents and moving things from the top to bottom and going back and forth between exponential and radical form, how about if my original function was f of x equals, say, 1 over x squared? Technically, that doesn't fit my power rule because my power rule said I need a base raised to an exponent. I have a rational function, but can I manipulate this algebraically and get a base raised to an exponent? Can I make the rational function go away? I can, right? Can I move this to the top and make it negative? All right, now, if I take this, x squared, and I move it to the top and I make it negative, did I take the derivative? I didn't, did I? All I did was algebraically manipulate it. So it stays f of x if I'm going to rewrite it algebraically. I didn't do any calculus. When I move that to the top and make it negative, I'm not doing any calculus. It's still the original function. I've just algebraically manipulated it. Now it's set up for power rule. I can do power rule. So I can do f prime of x at this point. Pull that negative 2 down in front. So negative 2, x raised to the, what's negative 2 minus 1? Negative 3. Am I allowed to have negative exponents? No. So negative 2 over x to the third. And notice how I kind of let this drop off. I let this drop off here. Once I tell them, hey, I've done the derivative, from here to here, it's algebra manipulation. From here to here, it's algebra manipulation. I've already told them I don't need to keep writing f prime of x, f prime of x, down, over and over and over. I mean, it just makes it faster. Okay, I can squeeze one more example right here, I believe. That's been known on this piece of paper. How about if I had f of x is equal to the cube root of x? Do I have a power rule? Is it set up for power rule right now? No. Could I manipulate it algebraically and turn it into it? Yes. X to the 1/3. Now when I do it, it's still f of x because all I'm doing is algebraically manipulating that, x to the 1/3. Now I can pull it down in front. So f prime of x, let's see, 1/3 in front. Now what's a 1/3 minus 1? I want you doing that in your head. It'd be minus 3 over 3, right? Negative 2/3. This is where if you can do that in your head, it's going to tremendously faster. Okay, now can't have that negative exponent, so I'm going to move it to the bottom. So 1 over 3. Now it'll be the, what's the root? Cube root of x squared. The bottom number is always the root. The top number then would be the exponent. So the cube root of x squared. Okay, but again, technically, are both those answers right? Yes, they are. I like this one better. Personal preference. Here, let's squeeze some more in here because I've got more room on the paper. Might as well not waste paper. All right, how about if I had f of x is equal to, what if they wrote a 4x squared on the top and then they just put the whole darn thing over 5? Is that really a rational function? What can you tell me about the 4/5? 4/5 is really the, you just said, Dane, what you thinking? You can just have 4/5 times x squared. That 4/5 is your coefficient. So really, if you don't like this, can't you write it like 4/5 times x squared? So no matter how they typed the question, I mean, think about legally, you can't just change things any way you want, but legally, how can you change things? Now I can easily apply the power rule. F prime of x, let's see, what's 4/5 times 2? 8/5, and then x raised to the first power, and I'm not going to put my first power on there. Well, shoot, I got more room. Let's just do another one on this piece of paper. Let's take a look at, say, f of x is equal to 1 over 2 times the cube root of x squared. 1 over 2 times the cube root of x squared. Okay, so am I going to have a lot of algebra manipulation to do first? Yes. All right, so probably I might turn this into an x raised to a fraction, okay, because ultimately I want to do that. Probably I would not do too many steps in your head. So this will be what, an x to the 2/3? All right, now can I do 1/2 times x to the 2/3? Can I do the same thing that I did over here? No, I can't, because my x is in the bottom over here, x was in the top. These two things are not equivalent. So I do not have a 1/2 x to the 2/3. I've got to take this x to the 2/3 and move it up to the top. So I'm still algebraically manipulating it. So, but I really don't even want to move it up to the top per se. How about if I just move it up, but keep my 1/2 out in front and say x to the negative 2/3? Is that better than putting it all the way to the top? Because I don't want it in the top either. Now, this one I think is, no, I did it here. What's 1/2 times negative 2/3? Can you do that in your head? 1/2 times negative 2/3? Negative 1/3. So f prime of x, negative 1/3, and then x to the, now can you subtract 1 there? If I subtract 1 here, I've got negative 2/3 minus 1. I want you to be able to do this in your head. Yeah, minus 3 over 3. Think 3 over 3 in your head. All right, negative 5/3. All right, I don't know. Can we have negative exponents? No. I'm going to go sideways here because I'm running out of room. So negative 1 over 3. How many steps can you do all in once? Can you immediately go to the cube root of x to the 5th? I mean, I don't know. To begin with, you might not want to do tons of steps in your head, but then after a while, hopefully it just kind of comes into play. I got a little bit of room. Let's do one more. I think the goal today is to see how many I can get on one piece of paper. All right, how about f of x is equal to, what if I did something like negative 3/2 x? It's in the right form as it sits, right? Has a 1 exponent right there, right? So 1 times negative 3/2 is negative 3/2, right? So f prime of x, negative 3/2. All right, now if I have a 1 right there and I subtract 1, that'll be a what? An x to the, so do I need x to the 0? Nope. Okay, so leave it off. So there we go. All right, now I did that with like individual terms. Did you notice that absolutely every one of those that I wrote down, single thing here, single, one little term, right, in each one of these. Could you apply this rule to a polynomial and do it multiple times? Probably you wouldn't want to, but probably we can. All right, so let's do it. Let's do power rule with polynomials. You got the hang of it. You understand how to do it with a single term. Now it's the exact same thing when I now give you a polynomial. You're just going to do it with the entire string of things. All right, and we don't necessarily want, I will do a couple of these, but I've been doing every function also with the function name of f. We all know they don't have to be all called f, right? Technically, so let's do this one with a g just to be different. All right, makes absolutely no bearing whatsoever. What if I had something like a negative x to the fourth over a 2 plus a 3x to the third minus a 2x? So I'm going to apply the power rule to my first term. I'm going to apply the power rule to my second term. I'm going to apply it to the third term. Okay, so I can just, this is going to be a negative 1/2 out in front, right? Okay, so I don't really need to rewrite that. I want you to just be able to see it. All right, so 4 times the negative 1/2, 4 times negative 1/2, 4 times negative 1/2, negative 2. Don't let me make a mistake. So negative 2x to the third, because we subtracted 1. All right, now do it here. Pull the 3 down in front. 3 times 3 is 9. X to the subtract 1 squared. There's an imaginary 1 right there. 1 times 2, 2. X to the 0, and I'm not going to write it. Okay, so it's the same thing, polynomial. You're just doing it of each individual term. Now, obviously, they're not all going to be that easy. They are going to give you stuff where, like, you got to put a little bit more effort into it. All right, how about if let's go back to f just because I like functions with the f name here. How about if they give you something that looked like 4x to the third plus 3x squared, and then all over x. That's got a quotient. So that one really is a rational function. All right, I'm not messing with my coefficients or anything here. That's a true, honest, legit things. All right, we've been seeing these in our limit problems. All right, what could I do to this? I'm adding on top. It's all over x. Could I break it up into like 2 individual fractions? If I break it up into 2 individual fractions, then I'm going to have an x in both of them, right? Because this is add, this is not multiply on top. So this breaks up different than what we just saw in the quiz. But then I'm going to have an x in the top and x in the bottom on each of the terms, then I can do laws of exponents and get down to just something raised to a power. All right, so algebraically, I'm just manipulating it here. Because it's adding, when I break this up, I need to have common denominators, right, to have added that to get a single fraction. So I'm going to have a 4x to the third over an x plus a 3x squared over an x. Whenever you break it up, stop and think. Can I then go take this and add them and get back up to what I originally started with? When you add fractions, you have to have common denominators. So that x plus x just gives me a single denominator of x. Okay, that's just the basic fraction algebra things. Now, laws of exponents here, this is going to be simplified what? 4x to the squared. Okay, so this becomes a 4x squared. Laws of exponents here, this becomes a 3x. Now, I've taken the rational function that they gave me, algebraically manipulated it down to this, so now I can take the derivative pretty nice. Okay, derivative what? 8x. How are we getting pretty good at this? So we can just go 8x plus 3. Seeing someone told you calculus was hard. It's not hard. Okay. All right. Oh, it'll get harder. Yes, this is just nice little baby introduction steps here, but we like baby steps. All right, now I know that because of COVID, we really didn't have a lot of our trig last year. However, trig's not going to go away. We're in calc, okay? So we're going to do, but again, we're going to do baby steps. We're going to do the derivative of sine and cosine. So we are just going to introduce this very, very slowly. Obviously, let's put a little note in here. You're going to have to memorize all of your trig derivatives, and ultimately we will have tons of them. But right now I'm just going to give you 2. Again, I'm going to use this notation because I want you to start being able to read the formulas in the book. All right, so you're going to see ddx of sine x. Okay, so that's saying I'm going to take the derivative of sine x with respect to x. I'm taking the derivative with respect to x. All right, sine x. This one, answer is going to be cosine x. Okay. Second one that we're going to introduce today, ddx. So I'm taking the derivative with respect to x of cosine x. And this one is going to be negative sine x. Now we're going to seriously do very, very baby steps here. I'm doing this. Obviously, this is not a composite function. It's just the sine of x. Nice little single sine of x. So in other words, we're not going to have anything like 2x or anything inside here. We're going to leave it initially just with plain x in there. Okay. So you're going to apply these 2 derivative rules to functions that have sine and cosine in them. So I could have an f of x is equal to maybe say a sine x over 2. All right, what can you tell me about the 2 down here? This is really 1/2 in front, right? So just so you can see it, we're going to have a 1/2 sine x, and I'm going to rewrite it that way for a reason. All right, a little bit later, which I'm not really going to introduce today, but we're going to have this thing called a constant multiplier rule. All right, that's just a constant out here. So I can look at this sine x, and I can take the derivative of sine x, and derivative of sine x is cosine x. So then my derivative, f prime of x, is going to be what, a 1/2 cosine x? Okay, so like when I said we're going to do super, super easy ones here to begin with, that's pretty super, super easy, okay? They will get harder, okay? We're just trying to not scare you off too much. All right, what if I did a polynomial function? Like let's do f of x equals, and I don't know, let's go like a 2x to the 4th plus a cosine x. Little 2 terms polynomial thingy here, a little trig function here. All right, can I take the derivative individually of these? And this one's going to be power rule, right? And then this is going to be this over here. So I don't need to do any algebraic manipulation. I can go straight to f prime of x. All right, now you're going to do this just the way we've been doing it. So this is going to be what? 8x to the 3rd. All right, so that one's not bad. All right, now this says plus cosine x. Derivative of cosine is negative sine. So minus sine x, minus sine x. And like I said, these very, very simple because of baby steps. We're doing baby steps. All right, one last thing. How am I doing on time? 7 after? So, oh, I got plenty of time. All right, one more thing. I don't remember. Did we've talked about the tangent line, right? And in pre-calc, I gave you circles and some information about circles, and then there was a tangent line, and I had you using pre-calc. I had you writing the equation of that tangent line, and we did it always with a circle, didn't we? Because we gave you the midpoint of the circle and a point on the thing, and you could write the equation of that tangent line. All right, so at this point, we got to realize that tangent line in calculus is extremely important, right? Tangent line, the slope of that tangent line, the tangent line is extremely important. So now what we're going to start doing is we're going to use calculus, and we're going to write the equation of the tangent line. And now that you know derivatives, we can start to introduce this. All right, so this will ultimately become a very, very important question throughout all of calculus. Okay, so we're going to say we're going to title this, finding the equation of the tangent line, because this is going to just be an overall theme that we're going to do over and over and over. Okay, so this is going to be what your questions are going to look like. They're going to literally tell you to find the equation of the tangent line to the graph of f of x equals x squared at the point, say, negative 2, 4. And we're going to do this using calculus. Okay? Now, first of all, just so I want you to get a visual, I want you to wrap your head around what this is asking you to do. All right, my function is x squared, right? We all know what that looks like, right? It's an upright parabola. The vertex is at the origin, right? So basically, I've got an upright parabola, and at the point negative 2, 4. So I don't know, negative 2, and then 1, 2, 3, 4. All right, let's just say that there's negative 2, there's 4. All right, they are asking you that at that point on the curve, they want you to write the equation of that tangent line. We're trying to come up with the equation of this line. Okay, that's a really sad tangent line I just drew, but you get the idea. All right, at that point on the curve, they want the equation of that line right there. Okay, now, the slope of the tangent line from like 2 or 3 days ago, the slope of the tangent line is the derivative. To write this, what do I need? I need two things, right? I need the slope of this line, and I need a point on the line. Do I have a point on the line? Yes, I need to find the slope. The slope of the tangent line is the derivative. So what am I going to do? I'm going to take the derivative of that function. That's my first step. Okay, so I'm going to take the derivative. So I'm deciding how I want to write this. Let's tell you what I'm doing here. Find the slope. Okay, so I'm going to take f of x equals x squared. I'm going to take the derivative. F of x equals, derivative is what? 2x, because we now know the power rule. 2x. All right, now, when I write the equation of a line, do I have slopes that look like 2x? No, I have numbers, right? What I want you to get in your head, this right here gives you the slope at any point along that curve. All right, so this is the slope at any point along the curve. Because we've already talked about the slope changes, right? Over here it's going to be negative something, negative something, negative something, negative something. When I come over here to this side, down here at the vertex, it would be, the slope would be 0. And as I come over here, they become positive numbers, but they change, right? It's a changing slope. This is the slope at any point. So if I want the slope at 7, I'd plug 7 in. If I want the slope at 1, I'd plug 1 in. All right, but I want the slope at negative 2. So I'm going to find the slope, the specific slope. I'm going to calculate the slope. So calculate, let's say calculate sounds better. Calculate the slope now. Now, pay attention to my notation. This is important. I want it at negative 2. Watch what I write. So f prime of negative 2. Function notation, that says I'm taking negative 2, I'm going to plug it into my derivative. Well, my derivative is right there. I'm going to plug it in. Negative 2 times 2 is negative 4. Do I need to show the here? Let's show the 2 times negative 2, which means 4. So my actual slope at the point that I am concerned with is 4. Negative 4, I knew that. Thank you very much. All right, negative 4. So I now have a slope. I have a point. And what I keep telling you last year was going to be your best friend, point slope form, right? Point slope form. So write your equation now. Point slope form. There is no reason to change to a different form. Okay, because it didn't tell me. So what do we got here? Y minus 4, don't let me screw up. Negative 4 times x plus 2. Now, if the